Hello, this is Manuel with Intagma and I'm here with a new Blender tutorial. Today I want to connect the dots. I want to create an effect that is known as the Plexus effect. I think because of an After Effects plugin that is called Plexus that creates this effect inside of After Effects. I want to take a point cloud and then I want to examine the distances between the points, and if these distances fall below a threshold, I want to connect the dots with a line. And by the way, this is the very first effect that I created as an Houdini tutorial on this channel, I think 4 years ago, and today is time to create the same thing inside of Blender using geometry nodes. So let's start by selecting everything and get rid of everything. Instead, I want to create a mesh monkey. Let's subdivide this monkey like so and then apply the modifier, and there will be the volume that I want to use to distribute some points in. So make this invisible. Now let's create a new plane that is just a placeholder object, and let's call it GN for geometry nodes and then connect the dots like so. Let's create a geometry nodes viewport and let's get rid of the side panel and create a new tree and call it GN underscore connect the dots like so. Let's cut this connection and let's bring in our Suzanne. Whenever you bring in another object, you have to decide if you want to use original or relative. I want to use relative because I want to use the global coordinates of the Suzanne points inside of the coordinate space of my object here. Now let's connect this, and this creates our original geometry now in this coordinate space. Now I want to distribute some points, but not on the surface, but inside of a volume. And to do this, I think you have to use the Blender 3.4 version that I'm using here currently. So if you don't find some of the nodes, please update to the very latest beta version. So I want to first turn our Suzanne into a volume using the mesh to volume node. This gives a volumetric representation of Suzanne. And now with this volume in place, I can use distribute points in volume, and that creates some points inside of the volume. I can up the density, and that creates more and more points, filling the volume with points. To develop the effect, let's go down to 10 with the density, or even lower, say 5, because as long as we have only few points, it's easier to understand what we will be doing. Now, this is our point cloud, and now comes the algorithm. To make this visually clear, I want to create a reroute here, and now let's invoke the N panel for a second, select the reroute and call it in. That is a point where the point cloud enters my setup. Great, let's cut this connection and let's put the reroute here. Before we start, let's think about what we are about to create. So if I have some points that are scattered in space, I want to start with the very first point. Let me create a new layer with a different color. So this point here should be the first point, and that has an index of 0. And now I want to examine all the distances to all the other points. So I can calculate the distance to this point and the distance to this point and the distance to this point and so on and so forth. All the distances, and as soon as I have the distances, I can decide if the distance is short enough to be drawn as a line. Now, once I have this, I have to do the same thing for the next point. Let's create different colors. So this, say here, is 1. Now I have to do the same thing and have to examine this connection and this connection and this connection and so on. This connection, and then the same thing for the next point. Dark blue, say, that is point 2, and we want to examine the connection to this point and to this point and to this point and to this point and to this point, and so on and so forth. So as you can see, to find all the connections between the points, we first have to run over all the points. So we want to examine point 0, and then point 1, and then point 2, and then point 3, and so on. And 4.0, we want to look at all the other points. So 4.0, we want to look at the connection between 0 and 1, and 0 and 2, and 0 and 3, and so on. And 4.1, we want to look at the connection between 1 and 0, 1 and 1, 1 and 2, 1 and 3, and so on. And for 2, the same, and for 3, the same. So we have a lot of examination to do. And if you look at this closely, we want to look at all the points for every point. How can we do this without loops inside of geometry nodes? Well, actually, we do have loops inside of geometry nodes, but these loops are not directly usable. Instead, we can loop over geometry only. So we have to create geometry to create this loop. And unfortunately, we cannot do nested loops. That is what I intended to do. I want first to loop over all these points, and then for every point, I want to loop over all the points. That is not possible either. So what could we do? Well, we can come up with a serialization. We could think about how to turn this into a linear loop. And if you think about it, we could do the following. We could look at point 0, and then we could pair it with point 0. And then we can look at point 0 again and examine the connection to point 1. And then 0 again, connection to 2. And 0 again, connection to 3. And so on and so forth. Let's assume that we only have 4 points at the moment. Now, after we did this, we examined all the connections of point 0. Now it's time to check the connections of point 1. So now we could look at point 1 once to examine the connection to point 0, then at point 1 again to examine the connection with point 1, and then again connection to 2, and again connection to 3. And after that, we can start with 2. So let's look at point 2 once to examine connection to point 0, and then with 1, and you get the idea. So if we do this, we look at every point, not once, but as often as necessary to go over all the points. And an interesting pattern is emerging here. If you look at this is the indices of the currently processed point, and this is indices of the target point that we want to examine the connection to. So we get an index pattern here that is 0, 0, 0, 0, and then 1, 1, 1, 1, and then 2, 2, 2, 2, and then 3, 3, 3, 3, if we have 4 points. And here we have a pattern that goes 0, 1, 2, 3, and then starts over at 0, 1, 2, 3. And if we have these two index patterns, we can match every point with every other point. And by doing so, we can circumvent the shortcoming of geometry nodes that it does not have nested loops. So let's get rid of the annotations and do this. So first we want to create some stand-in geometry that serves as a basis for our looping. So we want to add some points. For this we can use the point node that allows you to create points by count. And how many points do we want to create? Well, we want to create as many points as are in the point cloud squared, because for every point in the point cloud we want to create as many points as we have in the point cloud. Before we continue, let's quickly create another viewport up here and switch this to be the geometry spreadsheet. That makes it easier to debug things, and let's connect this here quickly. And you see at the moment we have 21 points. So what we need in total is 21 squared points. So first we want to find out how many points are in the point cloud, and we can do this by creating a domain size node. This gives us the point count. Let's connect it here and let's switch it to point cloud, and tells us that we have 21 points in the point cloud. And now let's square this using a math node. Math, and go to power here, and we want to use an exponent of 2. So let's square this number, and now let's create some points by connecting this to the count. Let's see. Now we have 441 points, so that is 21 squared. Let me check. If I put 21 times 21, we get 441. So 21 squared is 441. Okay, but these points do not have any location. We want to put the location of the point regarding their indices as an attribute on these points, to calculate with these attributes instead of the real point positions. Remember, this is just a stand-in geometry. It's just there to make geometry nodes run over 441 points. And we will just write the positions onto these points. But before we do this, we want to tinker with the indices. So let's create an index node. Index, and for debugging it's a good idea to use a viewer node, so let's create one. If you create a viewer node and you connect some geometry here, let me create some space here and make it visible, the attribute spreadsheet immediately switches to display the output of the viewer node, and now I can connect, for example, the index here. And if I now go to the points, we have a new field here called viewer, and here we see the index value, and the index value of course is the same as this index value here. Now, remember the pattern that we wanted to create. First, we want to create 21 zeros and 21 ones and so on and so forth. To do this, we can do the following. Let's duplicate this power node. We just need a math node and set it to divide. What if we take the index and divide it by the point count? So what that gives is a number 0, 0.0, 0.048, and so on and so forth. Let's see. And with 0.20, which is the 21st point, we get 0.952. And then we get a 1. So this looks suspiciously as if it is the right thing to do, but we are only interested in the integer part of this, not in the decimals. How can we just keep the integer part? We can duplicate the math node once again and set it to floor. The floor function will do just that. It will get rid of all the decimals. And now we have 0, 0, 0, 21 times. And then the first point in the next bunch is now called 1. And then with 0.42 we get a 2 here. And that is exactly what we need. So we now have an index number. The first 21 points are meant to represent 0.0. Now we need the second index for the target points. How can we calculate this one? Well, we just use another math node and take the index, but this time we set this to modulo. The modulo operator gives us the remainder of an integer division. So if I now create the modulo with the point count, let's see what this gives. And now we get 0, 1, 2, 3, and so on and so forth until we reach 20 with 0.20. And then it starts over at 0, 1, 2, 3. And that means now we have exactly the 2 index patterns that we need to match every point with every other point. To remember what we did here, what I like to do is to go to layout and create a frame, an empty frame. I use these as tags, as text tags. So the first pattern that we created is 0, 0, 0, 1, 1, 1, 2, 2, 2. If I assume I have 3 points, this is a pattern that I would create. 3 times the first index, 3 times the second index, and so on. Now let's duplicate this one, and this modulo creates a pattern that reads differently. It reads 0, 1, 2, 0, 1, 2, 0, 1, 2. That is what the modulo does. Now these 2 indices correlate every point with every other point in a long linear loop. Exactly what we wanted to do. Now let's start to compare the positions. For this we need the positions, but we do not have any positions on these temporary points. So we have to fetch the positions from the original points. To do this, there is a node called sample index. It samples a value by using an index, and we have 2 indices here. So let's switch this to vector because we intend to sample the position, and let's create a position node to tell this node which value to sample. Connect the position here. And now we want to connect the original geometry, the in geometry, to this geometry because we want to read values from this geometry. Add the index that we provide. Now connect this index to the index. This gives us our source position, because remember, this is always the same point, gives us a source position. Now let's do the same thing, but for the target position. We connect everything similarly in geometry here, but this time we use the second index. Now we get values for the source position and for the target position, and that means we can compare the lengths between these 2 positions by using a vector math. So create a vector math node and set it to distance. And connect the 2 values here. This now calculates the distances of all the connections between the points. And that means we now can compare if these distances are shorter than a certain threshold by using a compare node. So compare, and we want to compare this float value. It's a distance, so it's a float. And what we now want to do is we want to delete a point if the connection to its target point is longer than the distance that we specify. So let's keep this to greater than. And for now, let's put in something like 0.3 here. So whenever the distance between these 2 positions is larger than 0.3, we get a true. And with this true, we can do something. We can now create a delete geometry node. So let's feed in our temporary points. Let's move this stuff out of the way. Let's feed everything through this delete geometry node, and let's connect this here. And if I switch back to evaluated, you see we are left with 25 points. If I go directly here to the output, we have 441 points, but obviously only 21 points have connections that are shorter than 0.3. That is nice. But we have a second problem to solve, and that problem is that we have probably double connections, because if we have this pattern, remember we have 0, 0, 0, 1, 1, 1 if we have 3 points, and then 0, 1, 2, 0, 1, 2. We will compare, for example, the connection between 0 and 1 and the connection between 1 and 0. But that is, of course, geometrically speaking, the same connection. So we only want to have this connection once. And that is why I do a second test. And this test is, I want to test the indices. And I only want to keep the connection if the first index is smaller than the second one. That makes sure that I only use every connection once. And I want to test something else because it does not make sense to compare points against themselves. This will always be a distance of 0 and it will be drawn although the points are at the same position. So I want to get rid of these connections. How can we achieve this? Well, we do a second test, duplicate this testing node, and now we compare the indices. Let's compare the two indices by wiring them here, and now switch this from greater than to greater than or equal, because if both indices are equal, I want to discard this. So now we have a second test. We have two bool values. Both can be true or false, and we have to combine them. And to combine them, we want to use Boolean math, and we want to switch it to OR. So this port will be true if either this one or this one is true. So both can delete geometry. Let's connect this here and then the output of this to our selection, and we are left with just two connections. But if we now make the threshold higher, 0.5 for example, we have 14 connections. It seems to work because everything that resembles a connection that does not meet our tests is deleted. Now the problem is that we have points that resemble connections, but we do not have the actual positions. These points are just temporary geometry. They are all residing at the origin. So we have to provide the actual positions, the point positions, as attributes. So let's do this. We already sampled the positions, and now we have to write them to this geometry stream as named attributes, because the delete geometry node will tinker with the actual indices, so with the indices that Blender sees, and that means we cannot use these values directly. It will not work. We have to write them to the geometry. We could use a capture attribute instead. If you prefer, you can use that. But I think it's clearer to store named attributes. So let's create a store named attribute node. And let's switch this to be a vector and call the attribute myPos for my position. And let's put it here before we do the delete geometry. And then we need a second stored attribute, and that will be the target position. Because remember, every point here resembles one connection. So a connection has 2 points, a starting point, my position, and an end point, tar position. And the starting position will be this one here, the first one that we sample with these indices, and the second one will be this one that we sample with these indices. And now we have a lot of data here on our points, as you see, myPos and tarPos, and they are different. Not always, but they are different most of the time. And now this data is persistent after the delete geometry because it is attributes that are stored on the geometry. So even if the indices change, these values will be there. So we now can use them after the delete to create some lines and position the lines correctly. To create some lines, we just want to use instances. So let's create an instance on point node, and I want to create some lines. So let me create a curve line, and let's put the curve line onto these points. If I do so, I get 15 instances because we are left with 15 connections. Now let's turn these instances into real geometry, because then we have lines with a starting point and an end point, and we can use these points to connect the dots. So let's first use a realize instances here, which now gives us curves, 15 splines with 30 control points, and that is exactly what we need. And the good thing is, because of the way that the instance on point works, every line has alternating points. So the first 2 points are from the first line, and the second 2 points from the next line. And that means that you can tell if you are dealing with starting points or end points by the index. If the index is even, we have a starting point, and if the index is odd, we have an end point. And we can use this fact to set the right values. So let's first put down a set position node, set position, and let's connect it here. And now to set the position correctly, we need a switch node, because it now depends on if the point is even or odd, if we want to use the myPos that is stored on the point or the tarPos that is stored on the point. So let's create a switch, and this switch uses a Boolean value to switch between these 2 ports. And let's make this a vector. And now we want to read the the stored attributes, named attribute, and this one is myPos, and then let's duplicate this one, and that one will be tarpos. Connect both here. And now we need this switching value to decide which one to use, and that can easily be calculated by using the index, the remaining points, and deciding if it is even or odd by just using a math operation again that we set to modulo 2, because modulo 2 will be 0 if it's even and 1 if it's odd. And 0 and 1 is exactly what we need to switch between these two ports. So if we connect this here and now connect this here to position, the setup is finished and should work. But we don't see any geometry in the viewport, and that is because of the viewer node that is still active. Remember, we left this active, so if we just delete it, now we should get some output in the viewport, and it is working. Here you can see all the connections that we created. If we go to our test and up this value here, more and more connections are drawn between the points that we have. Let's go down to 0.5 again. We only get few connections because everything that is longer than 0.5 will get deleted. But now we can go to the very beginning and up the density on our point cloud to say 20. And you see you get a lot of connections because now we have more points and thus we have more connections that meet the requirements. And that is exactly what we wanted to do. Now let's create some geometry for these connections to make them visible. For this, I create a curve to mesh node, curve to mesh, to create geometry out of these lines. I need a second curve, a circle here for this node to work. So create a curved circle and connect to the profile curve. It is far too large, go down to 0.01. And you see now it draws the connections. But I don't want to have the connections only. I want to have the original points too. So let's go back to the beginning of our setup and let's create another instance on points. Let's just wire in the point cloud itself to this instance on points, and let's put spheres on the sphere. Icosphere will do here. Let's make this smaller, 0.01 for now. Now this is the points, and back here we have the lines. Time to join them. Let's create a join geometry node. Let's move this stuff over here, and let's wire in the points and the lines, merge both, and now with both merged, we can connect the output to the geometry, and we get both. The thing is we don't see anything because the lines are still too thick, so let's go down to 0.005 here. And now you see you get little spheres at the points and you get connections. Now we have a network. Pretty. Time to deal with the color. I would love to set some colors on the points and then make the connections interpolate the color. To do this, we first have to set up color on the points. So let's go back to the points and let's move everything before the in out of the way. And let's use some noise to drive the color. So let's lay down a noise texture. Noise texture. I don't want to use the color of the noise directly. Instead, I want to use the factor and then drive it through a color ramp. For this to work, let's first lay down a map range. As always, when working with noise, because the noise values usually are not evenly spaced out between 0 and 1. Let's go to 0.4 and 0.6 here. And now let's use a color ramp. Color ramp that will take these values and give them color. And I will use a dark blue here, and then on the other side red. And to make it more interesting, create two more knots, and the one in the middle will be yellow, like so, and this one probably green, maybe like this. Give it a little bit more fresh green here. This is too dull too, so this might look okay. So this is our color ramp. Now we want to set this color to our points to make it available in the shading context. And for this we use stored attribute again. So store named attribute, and I call it CD. That is a habit from Houdini, where the color on geometry is always called CD for color diffuse. Let's switch this to be a color, and let's connect the color here. And there's one more thing I want to do. I want to create a position field because I love to make the connection here at the beginning of the noise explicit. Now, a noise value is created for every point and is sampled, and some color is sampled and written to CD. That means that we probably can give some shading to these points. Let's switch to the shading editor and let's create a new shader and call it CD underscore instances, because this will shade the instances. And let's create an attribute node to read the CD attribute, but be careful, this is instances, these little spheres are instances, so we have to switch this to instancer to read the right attribute and put CD here, down there. Now it reads the correct attribute, put it in the shader. And we apply the shader to the point geometry, so back to geometry nodes. And up here, we can create a set material node, set material, like so, and switch it to be the CD instances shader. Now, if we turn shading on, you see that the points got color. Let me make the points a little bigger for you to see better what's happening here. So let's go here and let's up the rate to 0.02. And you can see now we have color on the points. Nice. But we want to take the same color for the connections, and we want the connections to interpolate the color. So if we have a green dot here and a yellow one here, this should fade from green to yellow. So we have the color on the points. How can we put it on our connections? We will need a second shader for this, and we want to sample the information and put it on the points just like with the positions. So here, where we sample the positions, we now need 2 more sample index nodes to sample the color information. Just duplicate them and set them up exactly like before. So the original point cloud geometry goes into geometry here and there. But this time we want to switch them to be a color. We want to sample color, so color and color. The indices are the same, so the first index goes into the first node and the second index goes into the second node, because we want to sample the point color and the target color. And now for the colors, we want to read the named attribute, because remember, we set this here to the points, and now we can read it here. So create a named attribute node, set it to color, and read CD. That is a color CD. That is a color on points. Now let's read the color and put it into these 2 ports. Now these nodes sample the color from the points. Time to put the color onto our stand-in points. So we have to duplicate these 2 stored named attribute nodes and do the same thing, switch it from vector to color. This time we want to store colors and connect them here after that, such that we have 4 of these nodes. I want to call the first attribute my color, my call, and the second one tar color, tar call, like so. And now let's connect the output of these sample nodes to the first and second node. Let's see what we get here. If we go to the vertices, we can now scroll over and see that I have my color and tar color, and both have values. Now I have these color values on the points that I used to create the connections. So I, in theory, could use them later to set the color to the point of the lines that we create from these connection points. Basically, it's the same setup as with the position, but after the position, we want to set the color. So let's move stuff out of the way. Here's our setup to set the position for the alternating points. And now let's do the same thing with the color. Let's create another store named attribute, because this time I want to store CD for the line points. And this CD will depend on odd or an even point. So switch this to point and do the same thing as here. We want to duplicate this switch node. This time, again, we want to set it to color. And now we want to read my color and tar color. So let's duplicate these 2 nodes and let's read my color, my call, and tar call. The node understand that this is a color value and switch the type accordingly. Connect this here and there, and then this goes into the CD value. Name it CD. So now the point of the lines have a CD value too, but they do not have a shader assigned. That is why you don't see the value. So let's create a shader, because remember, up here is instances, and we created a shader to read the attributes from the instances. But this down here is geometry, so we need a different shader. Go to the shader editor and click on this little 2 here to create a copy of the instances shader and just call it CD, like so. And let's see where the network is. Here it is. And the only change that we want to make is to switch to geometry, to read from geometry. Back to geometry nodes, and now the last thing that we have to do is to apply this material. So let's use a set material node here and apply the CD shader. And you can see as soon as we do that, we get color on our connections, and this color should in theory interpolate between the color values. But we forgot one thing. We forgot to connect the modulo value here, so it's not switching at the moment, it's just setting my call. But as soon as we connect our modulo value to the switch, now it sets the correct values and starts to interpolate the color, as you can beautifully see here with the blue dot. Now the color is just fading from blue to orange. Pretty. Now we are pretty much done. The last thing that I want to do is move the original point cloud to make the effect more interesting. I already got a noise there, so let's take this noise and use it for moving the points. That is easy. Here we have noise vectors coming out of this color port. We will need another map range node, but this time we want to set it to vector, and we want to connect this vector here, remap the values between 0.3 to say 0.6 to values between -1 and 1, because we want vectors that go in all the directions in Euclidean space that are possible. And we need one more node, a vector math node, vector math, to scale these vectors. Put it here, switch it to multiply. And for simplicity, I create a value because I intend to scale this uniformly. Connect it here, 0.5 for now. So now I have created noise vectors and I scaled them. Time to apply them. So after the store named attribute, we want to store the position. We can do that with a set position node. Put it here and connect this to the offset. And you see now everything is deformed by noise, and we have this control down here to tell how strong the effect should be. Very nice. Let's go to the render settings and turn off viewport denoising for now. Now, the last step is to make this move. And to make it move, I want to use a scene time node. So create one, scene time. And I want to use the second here to make the noise move. For this, I switch the noise to be 4D noise. That gives me this W value. And I can use this one to move the noise to the fourth dimension, actually changing the look of the noise in the remaining 3 dimensions. But if I connect the seconds here directly and then press play, everything is quite fast. So let's multiply the seconds down by using another math node. Add it here and set it to multiply and say 0.2. So now this will be slower. Let's test. Still a little fast. Let's go to 0.1. And now we got a very pretty particle animation of the points moving around, driven by noise, and the noise is shown as color. Now you can decide how many points you want to create. Say, let's go up with the density to 50, and you get a very intricate behavior here. We have a lot of control as we now can decide how far the points are moved apart by the noise, and you can tell which connections you want to draw and which you want to skip. Down here with the testing, where's our testing? Here's our test value. At the moment it's 0.5, but if we go higher, we draw more connections, and if we go lower, we draw fewer connections. So you see, you now get a lot of control to create this intricate connect the dots effect. So the last step would be to turn everything that is back here after the in and create a node group out of this. Then you could store it in the asset manager and make it ready for reuse later in future situations. Other than that, we are done. We created a Plexus effect inside of geometry nodes and colored it and made it move. So I hope you learned something from this tutorial, and as always, it is cheers and goodbye. If you like what we are doing, please consider becoming a Patreon. Not only for supporting Entagma, but for access to in-depth courses on topics such as particles, vellum, geometry nodes, and so on and so forth. And at this point, let me say thank you so much to all our existing Patreons. Without you, this channel would not be possible. Thank you.